Oh, perfect.
Okay, so the next speaker is Sai, and he will tell us about synchronization of time crystals outside the symmetric spaces.
Okay, thank you very much. Thank you very much, to the organizers, Abhishek, and all of the friends at ICTS, but also the non-local organizers here. It's a great pleasure to be here. It's one of the most fantastic series of conferences, and I always am very happy to be here. So I actually reported maybe a year and a half ago the previous version of this paper. So what I'm here to talk to you about today is exotic synchronization of time crystals outside of symmetric subspaces. I apologize for two things. One, I'm nursing a cough, so if I move away from the mic for a second. And the second is basically that this has only a tangential relationship to trajectories. It has a deep relationship, but I'm not going to talk to you about anything that has to do with that. So except for one or two slides. And so this is joint work with several authors who are in the audience, which I will acknowledge at the end. So let's get going. I understand there's also a slightly mixed audience. So what I'll do is talk to you about basically the field as a whole and just present the results in that context. So if you aren't particularly interested in this particular work, I hope to interest you at least in the field. So I'll talk about synchronization per se, and then I'll define these words exotic and also push it into the quantum regime. And then I'll talk a little bit about continuous time crystals and their relationship to synchronization before I present this slightly odd point about outside symmetric subspaces and then try and bring it all together. Okay, so classical motivations. So this is basically the idea of synchronization started with this little picture that many of us have seen if you've taken a course in nonlinear dynamics. It's basically two self-sustained oscillators which are held up together by a common board. And so, in general, the modern way that you would say this is that synchronization is the adjustment of rhythms of nonlinear self-sustained oscillators. So there's some kind of internal clock, like metronomes. There's something that keeps them ticking, and then, well, they're getting together is the story of synchronization. And synchronization is ubiquitous in basically all of nature. So, the human heartbeat, stability of networks, classical networks, circadian rhythm, these fireflies which blink in unison. It's all over the place in the nonlinear world, in the world that we live in. And so, of course, it's of deep interest to kind of scientists per se. And if we ever to talk about nonlinear systems in an honest way, then you can't get out of this kind of physics. Now, I first got interested in this because this is a slightly older one than that, but around 2010, people started being able to cool mechanical resonators, optomechanical, nanomechanical resonators down to its motional ground state. And just like David's talk just a bit before, the moment you can get something that's a classical technology down to the ground state, its relevant ground state, then you of course start having to engage with quantum mechanics very strongly. So a question that came up around 2015 or so is basically, what about synchronization? Because after all, these are mechanical systems. And in mechanical systems, just like these two will adjust the rhythm, I expect that something interesting will happen in the quantum as well. And that's the story I'm going to tell you about. Now, I just want to show you one thing in case you've never seen this before, which is that on this axis, which is traveling away, is basically the forcing amplitude, which is when you combine these two and put a coupling between them, you can then take the coupling as a parameter and turn it up or down. Or if you're pushing an oscillator from outside, it's just the force with which you're pushing. And what happens is that the region in which the second oscillator, the one that each of them talk to each other, well, enchain with each other or synchronize with each other, this only happens in a little frequency detuned space. And after that, they basically stop talking to each other because they're too far detuned from each other. And so this region can be expanded, so it's called an Arnold tongue. It can be expanded, and I'll show you several pictures which look like that. Okay, so that's the basic story. And here the word exotic, by that what I mean is two things. One is chimeras, which are basically in classical synchronization, comes out of this kind of picture in Greek mythology. But to us, they're basically just the coexistence of various synchronous subregions, basically, and they're emergent phases with some non-synchronous bits as well thrown in there. So if you have a collection of oscillators which can go around in a ring, then in the cleanest setting, what you'll see is all of them will synchronize to each other, but then there are physical reasons and physical settings. For instance, I refer you here, where you'll actually see them actually get into kind of different regions with synchronized and asynchronous regions. So this is chimeras. And the last kind of bit of exoticity that I want to introduce you to is what's called oscillation depth. And so this is basically where I could have physical systems which are oscillating, but then when you couple them and you put them in kind of some larger context, basically, the parametric variation that you've introduced suddenly makes the oscillations go down, and these oscillations then suddenly settle down into a steady state. And so these are called amplitude depth, oscillation depth, so on and so forth. And these two are the two pieces of exotic physics that I want to carry over from classical mechanics. Okay. So to go back to synchronization just for a second, this is the overarching view that I enjoy very much when I came across this paper by Garcia Morales et al. And Krischer. And I want to share this with you, which is that the notion of a phase invariant nonlinear oscillator. So if you just take the harmonic oscillator and you write basically p square over plus x square, and you write x dot is p and p dot is omega or minus omega square x, then what you can do is you can complexify this with a letter w, and you can write x minus ip, and w dot has a linear term there. Just ignore this guy for a second. Now, what you can notice about w is basically that it's phase invariant, which means if I perform a transformation which rotates the entire thing on the phase axis, then w dot remains unchanged. It's just the harmonic oscillators expressing the fact that the harmonic oscillator is a center. So what you can then ask is you can say, now give me a family of differential equations which are generalizations of this but preserve this property, phase invariance. And the very first term that you can add is something like this, because if you added a mod w squared w, when you did this transform, that e to the I chi would go everywhere exactly the same. That only appears in one chi, on one time. And so this is basically the first trivial example of a non-trivial example of a nonlinear oscillator, which is also phase invariant. And this is the Stewart-Landau oscillator. Now, why do we care about this in this conference? Because again, going back to the original motivations in 13 and 14 by Sadehpur, Bruder, Noonan, Kemp, and so on and so forth, they wrote this master equation down. So it's a harmonic oscillator with a drive, and then there are two dissipators, one of which is a nonlinear pump, and then a linear pump and a nonlinear damp. And if you write the expectation value of the annihilation operator, it appears exactly like the pin law that I just showed you. This is a phase invariant oscillator. And you can just plot the Wigner functions normalized suitably. And the black line there is actually the classical nonlinear dynamics of the mean field. And now what you can see is basically that when there is no synchronization, then this synchronization here refers to entrainment to an external field. Then there is no phase preference, it just goes all over. But when there is entrainment to an external field, then when the field favors a given frequency, then it locks in phase space with a phase with that phase. And you can see that there is a small dot here and a small dot here, which essentially makes the same story. So what is synchronized was actually a big question. And this was actually one of the initial parts of the last decade. This was kind of the thing that people were discussing. So for mean field, this is actually quite straightforward to say. And I'm going to use this. This is, in fact, what I'm going to use in the very last set of slides, which is in mean field, there is not much to discuss here. It's just classical synchronization. We can go back to it. But then if you know that the underlying system is quantum coherent, so on and so forth, then there is a larger story that you can build around this mean field synchronization. But in the true quantum case, just to kind of flash this point, if you look at several papers, what is synchronized is actually the power spectrum, the peak of the steady state power spectrum. And if the peak of the steady state power spectrum is actually locking on and moving with the external drive frequency, then you would say that you have some sort of synchronous behavior. You have to prove this, which was done. So what about finite systems? And this was a question that came up around 2018 because for a variety of reasons, but also just to kind of push this idea, this analogy as far as it will go. And so in the case of finite systems, actually, there was a suggestion. This is not fully accepted, but there is a suggestion, which is that qubits cannot be synchronized. And so I'll just leave it at that. And this has to do with basically the definition of the Houssy-Mikano Q representation function, and even the fundamental definition of what synchronization means in phase space. So you should have a free phase to lock onto, and the absence of the free phase in the case of the qubit, where the free phase ends up being basically the gauge degree of freedom that you can't see if you're in a diagonal distribution, basically precluded some set of authors from considering qubits as synchronization. Just a technical point, it doesn't do anything going forward for the rest of the discussion. But what does synchronization look like for, let's say, a 3-level atom? This is an SU2 representation of a 3-level atom. Not synchronizing looks like this. It's just a band which doesn't prefer any point along this direction, whereas this direction is the population direction. And so population is actually locked somewhere. There are some complicated Lindblad operators, which again are not particularly interesting for the rest of our discussion. But localization, phase localization looks like that. So when you see pictures in the literature, when you see Husimi-Q representation function, there's nothing special about it. You could do this with Wigner as well. Then phase localization exhibits itself in exactly the same way that I showed you with the Bruder van der Pol oscillator as well. Okay, so just kind of moving on, the first kind of one technology suggestion that we had made, and it's a very primitive technology suggestion, was to generalize all of those arguments to 3-level atoms, because we wanted to study the Scoville-Schultz laser heat engine, basically Maser heat engine. And what we pointed out was that the Maser heat engine is actually a synchronous system. So what I'm showing you here is the synchronization diagram. So I have taken a measure of synchronization, which is defined here, which I'm happy to talk to you about offline, but it has to do with the L1 norm of coherence for those who are more quantum information inclined. And what we did was we pointed out that this synchronization measure, if you plot it, along with the detuning to the external drive, reproduces the Arnold tongue, so it looks like there is synchronization here. But actually, you can connect it to the steady-state power spectrum of the laser. And so what we were arguing was basically that there are now measurable quantities in masers that people have worked with for 50 years now, which are actually signatures of synchronization, and that we should bring them forward and play with them to see if we can use them in the same way that all of the ubiquity of classical synchronization has been put to use. So directly on quantum synchronization, before I move on, I just want to make the following point. There are several experiments. So there is one by Christoph himself, along with Koppenhofer and Roulet, and this was a direct implementation on the IBM Q machine. And so this was one of the early experiments. And there are 2 more experiments which I was very lucky to be involved in. One involves rubidium, and this essentially shows synchronization in the stored coherences. And a more recent one with Mahesh, who's in the audience, on 4-level atoms and on a given molecule here, which you can read off. Okay. So with that small introduction, let me come to the relationship to time crystals. So again, time crystals are very briefly mentioned in a couple of talks, including Parvinder's. And so I'll give you a super brief introduction in case you're not from the field, but I'm doing it no justice. I apologize already. So time crystals are basically ideas that first Frank Wilczek proposed, and then they were kind of set into motion a whole amount of activity on whether or not we can see basically the breaking of time symmetries, and exactly that we see the breaking of spatial symmetries when we discuss the idea of crystals in space, just like crystal lattices. So in this context, basically due to issues with basically observing time translation invariance breaking in equilibrium systems, there were 2 ideas that came up. The first of which is the more famous one called discrete time crystals. And it involves basically periodic driving of open or closed quantum systems. And this is not the thing that I'm talking about. Instead, what I'm talking about is a different one called continuous time crystals. And this is basically, the idea here is that you have an open quantum system. Both its Hamiltonian and its Lindbladian are time independent. And so the dynamics is time translation invariant. Whereas if you look at the steady state, it's dissipative driven dynamics. For any finite size, the dissipative driven dynamics settles down into a time independent steady state. But if you take the thermodynamic limit, there is persistence of oscillations. So just in the thermodynamic limit and only in the thermodynamic limit, something funny is happening, that the thermodynamic limit is stabilizing oscillations and leaving this physical system oscillating. And so the ground state, or the steady state rather, of this physical system represents basically a breaking of symmetry, right? And hence a phase. So how you would solve for this basically is exactly the same way, which is that we go about any Markovian master equation, which is you vectorize the density matrix. You take the Liouville eigenspectrum, and the Liouville eigenspectrum informs you of all of the dynamics that you would want to follow. Here, let me just point out basically that because this is the steady states of an open quantum system, we don't care about all of these kinds of all of these kinds of eigenvalues which represent transients. So this is a pure decay. This is a spiraling decay. So you'll see the expectation value of some observer will oscillate down to 0. We don't care about any of these. These are the steady states, but we actually care about these, which are steady states which are accompanied by complex conjugate pairs of imaginary eigenvalues, and so there is oscillation in the expectation values of observables. So with this, I just want to say that this is exactly the same idea as basically 2D flows in, let's say, from Strogatz. So if you're, I just want to make contact with this diagram because I like it a lot. Okay, so with that, let me just say, if you took this idea very seriously, yeah, similar. Yeah. Yeah, so this is the traceful part. So the question that Sumilan is asking, just to kind of have the mic, is does the black dot, which represents the one that doesn't have oscillating coherences, imaginary part, coexist with the stuff that is in red? Typically, the black is always needed because it preserves the trace of the CP evolution. And so they end up being the diagonal part of the distribution. When there is basically oscillating coherences, they typically contribute to the off diagonals of the density matrix. And those off diagonals are oscillating. Okay. So what we did was basically pointed out that there are actually two kinds of, there is a reference missing here, I apologize. There are two kinds of synchronization that are actually possible in the literature. The first is basically this pure phase synchronization. And this phase synchronization is the very first set of things that I was talking to you about, which is synchronization being defined as basically the act of generating coherence in steady state and being related to L1 norms of coherence. And what we pointed out was that in the literature, there was this kind of need to talk about continuous time crystals and the fact that they're oscillating objects as synchronous objects, but they actually belong in a different class because this is actually not this guy that's doing the heavy lifting. It's this imaginary eigenvalues that are doing the heavy lifting. So you could ask the question, will they coalesce if you take several of these? I have one frequency here, another frequency here. Will they start talking to each other? And these are the kinds of questions that I'll show you quick answers to today. So with that, let me show you the paradigmatic model for time crystals. So this is continuous time crystals. This is the driven decay model. And if you don't like it, I'm with you. I understand the criticisms. It's a semi-classical model, but there are other generalizations of it which hold up a little bit better. So the idea here is that you have a drive part, which is a collective sigma x, and then a dissipative part, which is a ds minus. And to talk about thermodynamic competition, I just point out to you that there is a 1 over s sitting here. And this 1 over s basically means that as the dissipator size is growing, it's as the spin size is growing, the dissipators appear quadratically, s minus s plus, but there is a 1 over s sitting there, which actually makes it linear again. So in that sense, it's a little bit like Koch prescription, right? It makes both of these terms the same size and they're able to compete with each other. And so in the thermodynamic limit, you can see this again. So this is the Liouville eigenspectrum for the oscillation of the SZ magnetization derived from the Liouville eigenspectrum for finite sizes, 40, 80, 160, and then there is the mean field sitting here. And this is Yamini and several co-authors, including Sarofazio, who's on several of our papers as well. And so the transition between this non-oscillatory phase and oscillatory phase happens at a value which is omega over kappa equals 1. So omega is the drive, kappa is the dissipation. So in these kinds of normalized units of the Stoy model at omega over kappa equals 1, there is a phase transition that happens. So that's the entire story here. So what happens is that the mean field dynamics, basically, you can analyze, and I say this because I'm going to do exactly this. I'm going to imply exactly this for a later slide. You have a decay. You don't, so it's not pre-thermal in any way because the eigenspectrum, the gap closure is not like that. It's just a decay. It is 1 over n. So there's no, so what happens is that when you look at the eigenvalue spectrum, when you want to analyze the mean field dynamics, what you do is you look at basically the mean field equations along with basically the Jacobian for stability. And also you look for basically the fact that m square is equal to 1 because m is the normalized magnetization, right? It's sx divided by s, sy divided by s, sz divided by s expectation value. So this thing has to be bounded by 1. And this bounded by 1 makes these two red eigenvalues actually not the correct answer. and you get these two, which are the correct answers, and that's the exact transition that I just explained to you a second ago. So this is the maths of it at the mean field level. Okay, 15 minutes, good. Okay, so in this, and again, I'll skip past the slide because this is exactly restating all of this, which is that the oscillating coherences come and sit here, and then they take the, you take the expectation value of the initial state, and then these R mu's, the right eigenvectors, essentially are telling you what the subsequent dynamics look like. But, and in the mean field, what happens is that these beta mu's become, these beta mu's are the only surviving eigenvalues only in the mean field. So there is kind of essentially, an eigenvalue just goes and collides like that in the thermodynamic limit. So you have to wait till the thermodynamic limit. Okay. And the Liouville eigenspectrum, just for your pleasure of viewing. So, okay, so before I get on with the rest of this talk, there are already several experiments on this. I just wanted to flash just a couple of them. So this is essentially a cigar-shaped BEC that where people see oscillations. And you can see this is an attempt to make a continuous time crystal, which is supposed to be kind of a really robust and stable phase of matter. It decays for basically reasons that are outside of the theoretical modeling. So the experiment as a whole is a bit complicated. And if you read the experiment, it decays for. Likewise, there is another experiment here, which I won't say too much more about as well. And so to connect to this conference, I want to say, and this is part of the interest that I share as well, which is that you can ask questions about things like measurement-induced phase transitions and you know, and other kinds of dissipative phase transition physics questions at the trajectory level. And this has been done. This is not my work, but I just present to you that that there is basically conversation here about solving the post-selection problem and also solving the magnetization, looking at basically the magnetization photo count and homodyne trajectories for the driven decay model, the exact model that I just showed a second ago. Okay, and then just before I leave, I just want to say there are other models as well, but this is not the point of this talk, so I will just move on from here. And go back to try and motivate once more just what the point of this, this work is before I show you the final results. So we are interested in not just the fundamental phases, which we are, but also in trying to apply them to various contexts. So one of these is basically a network of continuous time crystals. This was basically reported a couple of years back by us. And here the idea that we were, I'll actually get to this point, but this is about network synchronization of continuous time crystals. And this is work done by Montenegro and friends on basically using continuous time crystals as sensors. And this is not even the only reference. There are several suggestions now about CTC sensors in the community. So as we're getting down this road, there are questions to ask about the dynamics, about the stability of these sensors and so on and so forth. And that's basically the small problem that we've tried to address. So before I get to that question, let me advertise two more pieces of work that we've done, which is related to this kind of broad question of trying to make CTCs and this kind of idea around this into kind of technology. So the first is, can they be synchronized with each other? Maybe we can signal boost them. Maybe we can begin to talk about CTCs the same way we talk about classical Kuromoto model. And the answer is yes. So just like you would imagine that if you took a supersaturated salt solution and you seeded a crystal in it, that this crystal seed would basically break the symmetry and then the rest of the crystal would form around it. We played the same experiment numerically. And theoretically, we showed basically in this paper that indeed several continuous time crystals coupled together can synchronize with each other, even if all of them are melted except one. And that one crystal that's melted, that's not melted, the active time crystal phase will actually activate all of the quiescent phases and pull them into a synchronous regime. And that's the cartoon here, that the Petri dish has one red active oscillator, and then it's pulling all the others in with it. Okay, and the next question that we wanted to ask was, can continuous time crystals actually be controlled? Can we put them in some sort of place where we can turn on and off the continuous time crystallization? Yeah. So in this case, we wanted to play the game with, so the main paper ties our hands to the back, and we only use dissipative coupling, and we show that this is still possible. And then, but in the supplement, we also do Hamiltonian coupling, which is much easier. So you'd imagine that if you're coupled with Hamiltonian coupling, you're actually boosting coherence. And you would imagine things are a little bit simpler. And that's what we found as well. Okay. So, so the next question we wanted to ask was, can continuous time crystals be controlled? Perhaps this is another step towards kind of making them into interesting controllable pieces of technology. And again, we answered yes. And this time by using the quantum Zeno effect. So we took a central spin model and proposed basically measuring the central spin very strongly, and this induces basically a continuous time crystal. This is indeed exactly what I presented last time. So I summarize this here as this phase diagram. These look like Klingon birds of prey for those who are Star Trek fans. Okay, so with that, let me get to the next, the point of my talk with 9 minutes left, which is perfect, which is exotic synchronization outside of the m=1 subspace. So this was published a month ago. And so what is the idea here? The idea here is, if you look at the standard literature till our paper, what it says is that there is a transition at omega over kappa equals 1. In fact, I even showed you the semi-classical analysis that produces this. You just solve for the mean field and then you solve the Jacobian, and that will give you the eigenvalues. The problem with that is that if you actually have dissipative processes, then dissipative processes usually do not preserve the full J subspace because they don't have to commute. If they're collective dissipators, then they sure. But if you have local dissipators, then they may not preserve. And this was the game that we were trying to push towards, to kind of make it a little bit more realistic, add one more little piece of real, hopefully real physics in it. So the abstract question that we ask is, if you had several subspaces out of which we combined basically some mixed state, some pulled up some mixed state of a density matrix and threw it into the time crystal evolution, what would it do? Would it simply just completely fall apart? Would it just not react at all? Would it not change at all? What comes up? And something interesting comes up, which is what I'm going to show you for the rest of this. And so this perhaps should have been the previous slide. So this is really what m not equal to 1 means physically, which is it's just local dissipators and so on and so forth. But let's say in the permutational invariant subspaces so that we can simulate them and so on. And so this is just the standard reference from Nathan Sharma. Okay, so this is a little bit of a, this is now I'm going to tell you about the simulation. So there are lots of moving parts, so let me tell you what we did. What we wanted to do was basically, first and foremost, if you took these equations, mx, my, mz, the mean field equations, and you set the m square, the total spin equals m square, which means that you're deriving it from some mixed state or something, or from lower sector. Could be a pure state as well, which is from a lower sector. Then what you can show, basically, is that the eigenvalues go as square root of m square minus omega square over kappa square. That's the reason I made this comment before, that for every value of m, we can actually show that there is a melted to time crystal transition, basically, at finite m. And all the way out to m=1, where we simply recover the Dickey physics that was done before. So that's the eigenvalue analysis. It's actually fairly simple. Now, what we wanted to do was test what this thing does in real life, and we wanted to do it with a kind of simple-minded view. So what we did was we took two ensembles. So what I'm showing you here is all of these black dots. Each of them represent a continuous time crystal. And this is just the mean field equations for a continuous time crystal, right? So I'm doing classical mechanics now. And what I've done is I've shifted the net m square basically back and forth around a mean value, which I've just called epsilon1. And so this mean is epsilon1, and then there is a red band here whose mean is epsilon2. And I choose some Gaussian distribution. I just pick some magnetizations from there, and then I can fix basically the dynamics of that. And the separation between them is some constant delta. Now, what I'm going to show you are basically two pieces of graphs which are side by side. And so I want to just show you the maths of it. I've already explained the physics of it. The first is basically that you can gain or lose correlations. And if there are subsystems which are correlated very strongly inside of a large physical system, this is what I refer to as chimeras. And so chimeras are these kind of blocks which are synchronized with other blocks which are either synchronized separately or kind of unsynchronized blocks as well. And the way in which we measure them, again, because it's a classical mean field, we could just do classical synchronization measures, and correlation measures are well known, the Pearson coefficient. And so this is just the time average Pearson coefficient, which just asks along the entire trajectory, is this correlated or not? And 0 is no synchronization, and 1 is complete synchronization in this case. So when you see the figures, I hope that this is how you read them. Likewise, you can ask basically, again, about whether or not these things are chaotic. And the way to do this is slightly technical, which is that you have to take two trajectories which are basically time delayed from a little bit from each other and evolve both of them and see if they get farther apart from each other. And so this is called delayed coordinate embedding, so which we did. And that's the Lyapunov exponents that come off of it is how I characterize chaos. Okay, so let me show you the chimera diagrams first. So what you're seeing here is these two little ensembles which are epsilon and epsilon 2, 20 uniformly sampled. I'll show you the next one, the number goes up to 100. But these are again classical differential equations. So you can push them to a little bit larger value if you care. But the point is made here. What you see is they're not coupled here. So, and what you see when gamma is equal to 0, gamma, perhaps you don't, I went through it quickly. Gamma is actually the coupling between the different time crystals. So when I take like these collections of time crystals, I couple them with the gamma AB, and gamma is how I talk about basically whether I'm coupling one sector to itself, one sector to another sector, right? I talk about all of this by just tuning the value of gamma. So maybe the first 10 belong to the first set and the second 10 belong to the second. Okay, so when the two ensembles are not coupled, you just see the time dynamics, right? Which is some parameters here underneath which are not very relevant. But as you tune the parameters, and you couple all of the oscillators together, but still they're disconnected from each other, which means that gamma is 0.35 inside the black collection of continuous time crystals, and likewise it's 0.35 inside the red, but the black and the red off diagonals are all 0. Then what you see is basically, you see time crystalline behavior and time crystalline behavior, but now they're beginning to lock to each other, and they're beginning to synchronize to each other. So it just goes back to the previous result that I talked to you about in a more general context, which is that continuous time crystals can synchronize with each other. Now, what happens is that when you now open and couple them, you see basically that there is one which actually has quite strong correlations, the black time series, but the red is falling apart. And you could see the exact same thing here as well. What I've plotted here is exactly, this is just the synchronous, this is the Carl-Pearson's coefficient. Everything is correlated to itself, so the diagonal is always just very dark. But what you see here is initially, when the two boxes are kept separate, you see a very large blue box here, which represents very large correlation inside of the black ensemble, and likewise very large correlations inside of the red ensemble, but the blacks and the reds are not talking to each other yet. And then when you open them up, basically the reds fall apart, basically. And so this is typical chimera behavior, classical dynamical chimera behavior. So what we found, let me conclude, because I have maybe 2 minutes left, is a complete phase diagram, and this is what I'm presenting in front of you, which is with a larger number of samples in our ensemble. And what we see is something very interesting. So I'm showing you two diagrams, so let me read through them. The left diagram is the Carl-Pearson coefficient, and the right diagram is actually this delayed coordinate embedded Lyapunov exponent. So you can't read, if you only computed this and stared at it, you would come to the wrong conclusion. If you only computed this and stared at it, you'd come to the wrong conclusion. You have to read them together, and this is the only point that I want to make. Because what you see is, as you detune the system, the two ensembles farther and farther, just like with the classic Arnold tongue, if the detuning is too large, I can't talk to the other guy, it's too far away from me. For the given drive strength, I can't talk to him, and I detune away from him. So what you see is synchronization falls apart as you go down this axis. If you couple stronger and stronger, you'll synchronize stronger and stronger. This is good. But what you see actually in the middle, in the intermediate regions, is if you look at the Lyapunov exponents, you see complete synchronization and very regular good behavior, but interspersed with regions where there is chaotic dynamics, basically. And there is oscillation death. And there are chimeras. And so this rich phase diagram basically means that if you wanted to use these clusters of time crystals as sensors, as network sensors, or to basically have a time reference, a classical time reference, all of these kinds of variety of questions that we hope to ask in the future, you have to be careful how you tune the parameters. And you couldn't just willy-nilly just keep delta low and tune the gamma up because you might hit a oscillation death region or a chaotic region. And so this informs us in that way, in a very simple fashion. So I'm done. So my bottom line is basically that CTCs can be synchronized. In the M equals 1 subspace, this leads to a variety of usual curiosities, which we have explored for about 10 years now in the literature. But outside of the M equals 1 subspace, because these are actually quite difficult to solve technically, this has been kind of one of the problems that's been open. And we haven't solved the quantum mechanical problem, of course, because simulability is quite a difficult thing here. But the classical mechanics of it definitely highlight that this leads to chimeras and chaos. And so we hope to kind of take this and apply it to things like sensors and things in the future. So thank you very much for your attention.
Thank you, Sai. Questions?
I have a somewhat basic question, and this is regarding the.
There is an online person who's talking. Just happens to be talking. Yeah, sorry, can you please go ahead?
Yes, a basic question about the definition of a time crystal. So in principle, even if you take an harmonic oscillator and which undergoes sustained oscillations,
yes,
could be a time crystal, right? I mean, and if you subject it to damping, then that time crystal is no longer there.
Sure. Yeah, so thanks for that question. So the answer is no, and let me just explain why. And so the idea is that time crystals are supposed to be phases of matter. And so if you look at the literature, there was a little bit of initial confusion on this. But if you look at the literature, the argument is that time crystals have to satisfy the following sets of properties. One is that there shouldn't be, it should not be a single body effect, because of course I can just take a spin on a Bloch sphere and take it for a spin. And that's not a time crystal. It should be something that is induced by many body correlations, it's stabilized by many body correlations. And that already is the answer to your question. I can't see who it is on Zoom, so I'm sorry, I'm just referring to this person.
Supurna.
Oh, hi, Sampurna. Yeah, Supurna. So there are several more. So there should be no fine tuning. So it can't be something that you've basically just, the moment you perturb a little bit the parameters, the whole thing falls apart, right? And there should be no special sensitivity to initial conditions, right? And there are some comments about avoiding things like period doubling and pitchfork bifurcations and so on and so forth as well. So in general, what I understand from this is that if it is a many-body phase of matter, it is stabilized by many-body correlations, which means if you turn off the relevant many-body correlations, the thing dies. And it's insensitive, it's not fine-tuned in any way, then perhaps you have a good candidate for a time crystal. So here you would criticize, Suparna, that this is a zero-dimensional model and it's a valid criticism. I want to just add to your.
Yes.
Yeah. But there are other models which have come up since, which basically are, do much better, which actually have two-body terms and stuff like that in them.
Thanks.
I'm keeping you from lunch, so your curiosity is competing with your lunch.
Can I ask you a question?
Yes, please.
Yeah. So, so you also mentioned some experimental realizations, and I was interested in realizations where you have multiple qubits. But it seems like because if you include the local dissipation that you have on every qubit, I think the fixed point is unique of the Lindblad equation, right?
Yes.
If that's part of your Lindblad equation, if it's sort of a
for finite
that
systems.
You can.
For finite systems. So the whole point about dissipative phase transitions is that in the thermodynamic limit, that's n going to infinity is a whole other limit you have to take. So all our usual understanding, which I think,
what I mean is that I thought there was a theorem that said if you have Lindblad equations in which your jump operators form a complete basis of the Hilbert space, that you only have one unique fixed point with eigenvalue 1, and there are none of these.
Yes. All of them. Yeah, okay, fair enough. So there are several points here. One is that theorem is very much true. This is Evans' theorem, I think, is very much true. And this doesn't compete with it because it's actually in a different parameter space. N is not discussed at all. And so this is in the thermodynamic parameter space. But the second thing is that all of these, to directly answer your question, if you have a Lindblad operator, no matter what space you're in, if you need strong symmetries of the Lindbladian for you to arrive at these, and that protects us from errors.
Right, but do you see this? Okay, so maybe, you know, because you mentioned some implementations, but those were more for large spins, right? But
yeah, but they were in Dickey.
experimental?
They were Dickey kind of implementations, collective
Yeah.
spins.
Okay, but like for say superconducting qubits, where would there be a
Yeah, I mean, if you can get
possibility
into a Dickey subspace of a superconducting device, you could do this exactly. There are other models as well, so I'm actually doing myself a disservice by saying it this way to you. But in principle, it's, you should be in as much as, so let me say it this way: in as much as Josephson junction arrays can simulate a plethora of different condensed matter systems, I could show you exactly what models there are, and it's more or less a straightforward implementation to
I
it.
see.
Yeah,
Okay.
yeah. But the question is basically that because it's a phase of matter, you would have to take thermodynamically large numbers, and at least I don't know what the.
Yes.
Yeah.
Hi. I'm concerned about this sensitivity you just commented about, like in thermodynamic limit. Thermodynamic limit, like your dissipation goes to like 0, and so your
It
model,
doesn't.
yes, like 1 by s.
Yeah.
So your model should not have any sensitivity, right? So
Sensitivity to what?
sensitivity means like this omega, you are like omega sigma x in your first order.
Yeah, sorry. Let me just maybe be a little bit careful about what I'm saying when I say sensors. Is this the question about sensors, sensitivity as in sensors is your worry?
I'm worried about your initially you are using this one, yes, this sigma, the capital sigma sensitivity.
Capital
Sigma.
This one.
Yeah.
This one. Yeah. So no. So the point is the thermodynamic limit is funny here. So let me just tell you what I. So Sx is extensive in the number of atoms. So Sx appears once, just when you multiply the Sx rho Sx, right? It appears once on this side. If you just remove this k over s just for a second, s minus appears twice. It appears as s minus rho s plus, and then anti-commutator has the quadratic term in it. So what happens is that if you just solve this for any finite size, the number of atoms basically, if you think it's multiplying the second term quadratically, whereas it's only multiplying the first term linearly. And in any size, basically the dissipator wins. So when you divide by s and you take the thermodynamic limit, you can't just say it goes to 0 because there's actually a quadratic s minus sitting here. And that's the way I would interpret, heuristically make this argument to you here. Yeah. And so everything is sensitive all the way down to the.
Maybe I missed this just for the confirmation because I didn't get the sense that what kind of, how to choose the Lindbladian dissipators if I want to see a continuous time crystal. What kind of exact operator shall I choose?
You can just do that. That'll work.
Yeah, I mean, but in general, what structure is producing this effect?
There are some algebraic conditions. So essentially the story here is, so maybe I explain it here. So the point is basically that for any finite size, when you solve the Hamiltonian, when you take the Liouvillean, the Lindblad equation and you write the Liouvillean for it, the Hamiltonians basically produce the plus minus imaginary eigenvalues. And the Lindblad operators go all over the place, like they produce all of the dissipative stuff. So what you need is some specific algebraic relationships between them that also have like a thermodynamic limit. So for synchronization, this is known what the algebraic relationship is. This is due to Bucha. But I think in the CTC, in the time crystal case, this has not been fully kind of worked out. So if you give me a Lindbladian, if you give me an open system evolution, I can more or less tell you whether or not this thing will have a phase transition. We've tried to solve the problem of reverse engineering it and kind of ran into algebraic dead ends. But it's a good question, yeah.
If there are no more questions, we can thank Sai again.
Thank you very much. Yeah.
And Abhishek has an announcement.